Hello. In this video, we'll be talking about how to factor polynomials using the greatest common factor and the grouping method. Let's get started. So to begin, let's remind ourselves how we would take a binomial times a binomial and multiply those together using what we called the distributive property. So if we had, for example, 2y minus 5 times 3y plus 1, we could multiply those two binomials by distributing our 2y to each of the terms in the second binomial. So 2y times 3y, remember how we do that? 6y times y is y squared, because there's two copies of y present. And then 2y times 1 is just positive 2y. Then we could also distribute the negative 5 times each of the items in the other parentheses, right? So if we take that negative 5 times 3y, we're at negative 15y. And if we take the negative 5 times the positive 1, we're at the negative 5. Combining like terms allows us to now have a trinomial, meaning 3 terms instead of 2 terms. So our first highest power term would be 6y squared. The 2y plus the 5y are like terms, so we can add their coefficients only. 2 plus 5 is 7, so I have 7 copies of y. And the negative 5 is our constant. So 6y squared plus 7y minus 5 would be our trinomial. That means the same thing as the binomial 2y minus 5 times the binomial 3y plus 1. So that's a skill that we remember from the past, that we can multiply two binomials together using the distributive property. Now what if we wanted to deconstruct the trinomial? So we have a trinomial here, 6y squared plus 7y minus 5. When we ask you to factor, that's what we're saying. What times what? What two factors when multiplied together would produce this product, this trinomial? And today we're going to introduce the greatest common factor to allow us to have a place to begin. And then we'll teach you other techniques in this video and in the next one. So we remember that another way of writing what we just did was called foiling. First, outer, inner, last. It's basically just distributing over and over again. Your first terms, your outer terms, your inner terms, and your last terms. All right, so let's head over to our next slide, where we talk more about factoring. And we say that the process of rewriting your polynomial as a product of its factors, so that means multiplication, right? As a product of its factors is known as factoring, okay? So when someone asks you to factor, that's what they're saying. Deconstruct the original expression, however many terms it has, into something times something times something times something, right? And it might just have 2 factors, but it could have more than that. Now keep in mind that the main reason students struggle with factoring isn't necessarily because they don't understand the steps to factor, right? The algorithm, if you will, but it's mostly because they struggle with their basic multiplication facts, their multiplication skills. So I have in this video, in the actual notes for this video, you'll see that there is a link provided where you can find a list of resources, a lot of applications on your phones, which would allow you to practice getting your multiplication skills up. So you want to work on that, invest the time in getting fast with multiplication because it's going to save you in the long run as you move on in algebra. Okay, so to factor completely, the first thing we're going to be doing in our first box here is we're going to be looking for a greatest common factor. Is there something that is shared by every single term in this expression? If so, we always factor that out first. Then we'll look and see what kind of situation is left as our second factor. So once we've done that, we'll notice, well, maybe there's 2 terms remaining. Maybe there's 3 or 4 terms, and we'll be able to analyze what to do next. So let's take a look at our example here. We're told that we have 12x to the 5th power plus 18x to the 4th power minus 24x to the 3rd power. And we're asked to factor out the greatest common factor. So we have to look at all 3 terms. This is a trinomial, 3 terms. The degree right now is 5. Its highest exponent is a 5. But to factor out a GCF, we would first look at the coefficients. Do they share any common factors? Well, 12 is divisible by 2 and 3 and 4 and 6, right? So 6 is the largest number that goes into 12 other than 12 itself. And also 18, that's divisible by 1 and 2 and 3 and 6 and 9 and 18. Notice I said 6 in both of those numbers, so that might be the largest number so far. And negative 24 is divisible by 1 and 2 and 3 and 4 and 6 and 8 and 12, oh my, and 24. So again, you heard 6 in all of those. You could have written them out if that's helpful for you. But I noticed that a 6 is the coefficient that goes into all 3. What about the x terms? How many x's do they all have in common? Well, x to the 5th, that means that the first term has 5 copies of x. X to the 4th means that the second term has 4 copies of x. And x to the 3rd means that our third term has 3 copies of x. So how many x's do they all share? X cubed. That's right. So if you factor out the 6x cubed that they all share, in the parentheses, we would write our factor that you'd be multiplying it by. So let's see what that would yield. Basically, you're just dividing each term by 6x cubed. 6 goes into 12 2 times, and x cubed times what gives you x to the 5th? Well, you could just subtract the exponents. 5 minus 3 is 2, so you'd get x squared. And that should make sense. When you multiply x cubed by x squared, the exponents get added up, and you get x to the 5th because there's 5 copies of x. 6 times positive 3 gives you positive 18, but you're going to need another x, aren't you? Because we only had x cubed pulled in front as our GCF. And finally, 6 times what gives you negative 24? That's right, negative 4. So then you would take negative 4 times 6x cubed, but that only gives you negative 24x cubed. You need to have what power? Oh, that's right, you just need x cubed, so you're golden. Now, if you needed x to the higher power, you might need to actually write x to another higher power. But in this case, that's all we need. So we are in great shape. We have factored out our GCF in this expression. Now, this is the beginning of every factoring problem. You want to always start with looking for a GCF, which is what we did first, and factor that in front. Once you've done that, you're then going to ask yourself, what's left in parentheses? Do I have anything else that I could factor? Well, what we see here that's left in our parentheses is called a trinomial. So with this trinomial, what you're going to be learning about in the next video, not in this video, but in the next one, if you're curious, you can watch them both. In the next video, you're going to be learning about how to recognize different ways to factor trinomials. Sometimes you can factor them further, sometimes you cannot. So that would be the next step that you would be talking about typically in a factoring problem, going further. Some other types of situations that we're going to run across today and in our next video are the difference of two squares. So let's suppose that in parentheses next to 6x cubed, you had something squared minus something squared. If you have that pattern, this will be easy to factor. It'll just be a plus b times a minus b when the first item was a squared and the second was b squared. And you can see why. Go ahead and check by foiling, pause the video, and you'll notice that your middle terms will cancel out. Also, a difference of cubes, we're going to see that in our next video as well. If you have something cubed minus something cubed, you're going to end up with the something minus the something, so the things without being cubed first, a minus b, times the something squared, a squared, plus their product, ab, plus b squared, the second thing squared. So we'll be talking about those patterns coming up in the next video. So the sum of cubes works exactly the same way. You'll just notice that the sign gets switched so that the right terms cancel. But what we're going to focus on in this video will be the following. We're going to notice that if I have 4 terms, I could try factoring by grouping. So if I had 4 terms left in the parentheses instead of 3, I could try factoring by grouping. Otherwise, with the 3 terms, we're going to need other methods that we'll learn about in our next video. So I would recommend that you write this box down. These are the different types of things we're going to expect you to know how to factor by the end of these 2 videos. All right, let's continue to our next slide. Here we get another practice example with greatest common factor. It says factor out the GCF, negative 4x squared minus 8x plus 12. All right, so I'm going to encourage you to pause the video. It's just like the one we did on the last slide. See if you can find the GCF for yourself and begin that factoring process, and then come back and see how you did. All right, let's see how you did. Did you notice that each of these 3 terms shared a number, a factor of 4? Now you could choose the positive or the negative. Typically we do factor out a negative if our leading coefficient is negative, so that's a little trick. So if we factored out the negative 4, that's going to be most helpful to us. Now notice I left a little bit of space next to the negative 4 because it could be the case that there is an x that they share in common. Now what some students notice is that the first 2 terms do share an x, so it's very tempting to want to put an x up here. But the third term does not. It's only a constant. There is no variable x. So therefore, I actually should erase that gap and just put the parenthesis right next to the negative 4. So let's see what you did. After you factored out that negative 4, you should have said, negative 4 times what gives me my first term? Yeah, that's right, just x squared. Well done. How about negative 4 times what gives you negative 8x? Yep, positive 2x. Great job. And finally, negative 4 times what gives you 12? Yep, negative 3, that's correct. Okay, so what we've noticed here is that we've factored out our GCF of negative 4, and this is what we got after factoring out the GC, it's an ugly C, but the GCF. Okay. Now, technically, what we're going to be doing in our next video is saying, okay, now I have a trinomial, 3 terms in parentheses. Can I go further? Right? And so what we can see here is that you will actually have the ability to factor this further once you have the methods from our second video. If you're curious and you want to try it yourself from what you think you remember, the answers that you should be getting is -4 times x plus 3 times x minus 1. Okay, because the product here is -3, and when you add up 3x minus 1x, you get 2x. If you have no idea what I'm talking about, it's okay. We're going to refresh that in our next video. But if you already remember that, I wanted you to be able to know the final answer for that problem. Okay, now in B, you might be wondering how that is anything like A, because A was nice and simple, right? You had your nice 3 terms. It was just like your previous example. But this is where we have to actually start to think. We have to think, okay, she says there's a greatest common factor. It looks a little different than last time, but could I try to find something that these terms have in common? Let's try it on your own. See if you can come back and talk to me in a second. Okay, did you notice anything that they had in common? Yeah, technically each term, there's one term here and there's one term here. Each term shared something in common, didn't they? What was it? Yeah, you can see it. It's 2y minus 5. So that GCF here is 2y minus 5. So when you factor that in front, parentheses, because it's 2 items, 2y, more than one item, we use a parenthesis, 2y minus 5. Open up your new parenthesis, and what would go inside? Let's think about it. Well, the first term had 3y next to it, right? So we're going to need a 3y there, because when I distribute, I would get the original first term, right? 2y minus 5 next to 3y. But what is the coefficient of our second term implied to be? It is 1. Good job. That's kind of hard for students to see sometimes. If you don't have a coefficient, like if I just had x, what is its implied coefficient? How many copies of x do you really have? 1, right? So anytime you have a term with nothing as its obvious coefficient, it must be a 1. So that means then I would need to put a +1 here. Now, if you didn't see that, it's okay for today, but in the future, you're going to need to see that. Here's why. If you forget the 1, what you've really done is you've deleted the second term, haven't you? Because all you would have is 2y minus 5 next to 3y, which is nice, but that's only your first term. So by putting the 1 there, you would eventually distribute to both of those terms, wouldn't you? And that would give you your second term, which is why it's very important to recognize that the coefficient here was 1. So that's kind of tricky. I'm going to encourage you to put a note there and practice doing problems like that in your homework so that you can feel very comfortable recognizing that 1. Okay. All right, so we practiced an example where we've taken out the GCF, the greatest common factor. Let's now talk about that next approach when we have 4 terms or more, called factoring by grouping. So 4 terms or more, now I put 4 plus here in my notes. There's a little caveat there. Technically, it could be 4 terms, 6 terms, 8 terms. You get the idea, perhaps. If you can group them into an even number where you basically cut the number in half, 2 and 2, or 4 and 4, etc., 3 and 3, then factoring by grouping could be a way to start off the problem. Keeping in mind that for all of the methods that we're about to show you in this video and the next one, the first step in your factoring process, that algorithm, should be to look for a GCF. If there is a GCF, you're going to have a lot smaller numbers to work with, and you're going to be very thankful. So always look for that GCF. So I begin looking at an example with me. Look at an example with me here in the middle. I begin with the polynomial x to the 3rd power plus x to the 2nd power plus 2x plus 2. That has 4 terms, doesn't it? So it's not a trinomial, it's not a binomial. It's technically a quadnomial, but we don't usually use that any special prefixes like that after the trinomial. We just say a polynomial with this many terms. So we have a polynomial with 4 terms, and that means it is fair game for potentially using this grouping method. The first thing I do after recognizing it has 4 terms is I look for a GCF across the whole problem. So I survey the problem and I say, is there a number and a letter, or a number or a letter that they share in common throughout the whole problem? Well, not really, right? If they all had an x, for example, then the GCF could be x. If they all had a factor of 2 for a coefficient, then we could pull out a 2. But not all of them share those things. So instead, we notice there is no GCF. So if there's no GCF, then you can continue looking for another way to factor potentially. And I noticed that because I can use the grouping method, because there's 4 terms or more, I can group them into 2 by 2. Most students will probably group the first 2 and the last 2. And in this case, that works very nicely because each grouping, you can kind of see what the greatest common factor of each pair would be. But sometimes those pairs aren't the best choices, so you are allowed, keep in mind, you are allowed to group the first with the third and the second with the fourth, or the first with the fourth and the second with the third. You don't have to just do the first two and the last two. So it doesn't have to be boring, but you are looking ahead. What pair is going to be nice for a good GCF to pop out? Okay, so now that I've grouped them, we notice that the first pair has something in common. You're right, x squared. So I pulled out the x squared as its GCF. So that's what I'm doing. I'm finding the GCF of each grouping. The second pair shares a 2, so that's what I pull out here, a positive 2, to be specific. So once you factor out the x squared, what would remain for those two terms in front? Just x plus 1, because x squared times x is x cubed, and x squared times 1 is x squared. So we're back to where we started, making sense. Similarly, 2 times x is 2x, and 2 times 1 is 2. So what's the point of doing this? Kind of seems strange, right? Well, the whole point of doing the grouping method is that once you've paired them up and factored out their respective GCFs, if it's truly factorable, not prime means it can't be factored, right? If it's truly factorable, you should spot a new GCF of these two terms. Kind of like the last problem we did in part B, where they had like 2y minus 5 in common. These ones have the binomial x plus 1 in common, don't they? So there's the binomial x plus 1 that they share. So you can factor out that common factor of x plus 1. Now what would be next to it? Well, whatever is next to it here. So here it was x squared, so we put x squared in parentheses. And here it was plus 2, so we put plus 2 in parentheses. And so we end up with x plus 1 as one binomial factor times x squared plus 2 in parentheses as my second factor. The great news about factoring, you might not see it as great because it's more work, and we don't like work as Americans typically, but the great news about factoring is that you can know you're right. You can actually take the time to redistribute x times x squared is x cubed, x times 2 is 2x, 1 times x squared is x squared, 1 times 2 is 2, and what you'll notice is you're back to the original problem. So you know that you're saying the same thing in a different way. In numbers, not in polynomials, if I had, for example, the number 12 and I wanted to factor it, I could call that 1 times 12. Those are two factors of 12. It means the same thing. 2 times 6, it means 12. 3 times 4, it means 12, right? We can say the same thing in lots of different ways. And factoring is another way to say the same thing that will be beneficial to us as we start solving equations and looking for x-intercepts on graphs. So there is a purpose. We are going to learn the purpose in the coming days of this course. But for now, you have to take my word on it for it. This is one of the skills you need to invest your time learning. Most students who struggle in their future math classes don't struggle with the content itself, but they struggle with the early discipline of knowing how to factor, which also depends on multiplication tables. So you are going to need to practice those skills so that you can become really strong and competent and confident with your math problems. Okay, enough of talking, let's go practice. Here we go. Example 2. Factor by grouping if possible, because it's not always possible to factor. Sometimes it's prime. So in A, we've spread out the polynomial into 4 terms. Technically, you might notice that these 2 terms in the middle could have been added together. Those are like terms, but we're trying to make it obvious to you that there's 4 terms. We could use the grouping method, okay? So if I wanted to begin this grouping process, which 2 terms do you think we should maybe group together? Any suggestions? Well, yeah, if you said the first 2 and the last 2, that's definitely a valid option. Most students would probably choose those. Notice you could have also chosen the first and the last. The 3's kind of look nice together. But the middle terms, 18x and 5x, they don't share any nice numerical GCFs, but they do share the variable x. So there is a way to proceed using those methods as well, those pairings as well, I should say. But I think most of you probably would have chosen the first 2 and the last 2, so let's go with that. So that would mean then that the GCF of our first grouping is what? Good, a 3. And what about the variable? Do they share any variables in common? Just x? Good job. And what would that leave us with in the parentheses as this other factor? Yep, it would lead us with an x, great job, plus a 6. You got it. That's right. Now what about the second grouping? What should we factor out of that pair? Okay, so you see a 5 in common, and it's positive. Now this is where students have a little bit of difficulty. Sometimes they'll see a negative 5x, and they're not sure if they should factor out the negative or the positive. The great thing is, if you pick the wrong one, you'll know soon enough because the binomials won't match, and then you can just make that change and everything will work perfectly. So there's no stress here. Pick either one, positive or negative, and if it doesn't work out, just change the sign and you'll be golden, okay? So I chose positive because this was already positive, so it was kind of obvious, right? So I choose a 5 to take out, positive 5, and that would leave me with what inside? Yeah, x, because 5x is what we had there, and 6, positive 6, because it was 30 originally. 5 times 6 is 30. Okay, what did we do now that we have factored out the GCF of each pair? Yes, we looked for the new GCF, the binomial that they have in common. This is the step where if factoring was not possible, they would not match. Now, if they were just off by signs, it probably was this sign issue, right? If these were both negative, you could just change the sign and everything would be fine. But if it's not a simple sign error, if they're completely different, then that means you have a prime polynomial and it can't be factored. Okay, but we do not have a prime for us this time. We have an x plus 6 that they share, which means that the final answer should be, which you could check, x plus 6 times 3x plus 5. Again, where am I getting those numbers from? Those were the coefficients of the binomial, right? 3x plus 5 are those coefficients. We're just adding those coefficients up. We're factoring out the x plus 6 GCF that they share. Again, you can know that you are right if you take 2 seconds to check. X times 3x is 3x squared. That's this term. X times 5 is 5x. And 6 times 3x is 18x. So 5x plus 18x, little mental math, that would have been 23x, but we've also spelled them out already for you originally, 18 and 5. Last term is 6 times 5, that's 30, so I know 100% that I'm right. There's no need to guess. In fact, if you get one of those wrong, it's going to make, excuse me, it's going to make your future algebra problems impossible to get the right answers. So you're going to need to have the ability to know that you're right. Okay, try B on your own. It looks a little bit wonky, but it's the same exact type of problem. All right, let's see how you did. So if you grouped two and two together, perhaps you chose the first two and the last two. That's definitely fair game. I think probably the worst pairing would have been the first and the fourth and the second and the third, because v to the 6 and 35 don't share anything that's obvious, right? So maybe you did try the first two and the last two again. What do the first two share? Right, they share no numbers, but they share variables, don't they? V to the 4th, they both have 4 copies of v. And what would the binomial next to it be? V to the 2nd, great job, because v to the 4th times v squared, you add those exponents, there's 6 copies of v. Minus, great job, 7, and would there be any more v's? Nope, not this time, because that's just going to give you, if you distribute 7v to the 4th power. So that is good. What about the second pair? What do they share in common? Well, good, they share a 5, but it could be positive or negative. Let's try the negative and see if it works to our benefit. If not, we'll change that sign. So no need to worry about that sign. We're going to choose negative for now and see what happens. Usually that's what I'll do. I'll just take the sign I see there and put it right down here. And if it doesn't work nicely, I'll change it. Okay, so if I put the negative 5 there, what would be in parentheses if I take out the negative 5 as a GCF? Wouldn't it be positive v squared then? Negative 5 times v squared is negative 5v squared. We're golden. Negative 5 times what? Watch yourself here. Negative 5 times what gives you positive 35? Good, a negative. I was hoping you'd say negative, not positive. Negative 7 is correct because a negative times a negative creates a positive, doesn't it? Now, the beauty of this part of choosing the negative 5 is that we have exactly the same binomials now, don't we? So this is something we've seen a few times now in this video, which means we're going to be able to factor out that binomial they share in common, v squared minus 7. This is a very important skill if you're going on in algebra and calculus, the whole sequence. We are going to see this over and over again, recognizing things that we can pull in front they share in common. So that's v to the 4th minus 5. Once again, you don't have to hope you're right. You can know you're right. V squared times v to the 4th, that's v to the 6th. V squared times negative 5, that's negative 5v squared. Negative 7 times v to the 4th, negative 7v to the 4th. And negative 7 times negative 5, positive 35. You know you're right. And that's going to be super important to know that your answer is correct before you proceed in a harder problem, especially when you get into applications and word problems. Okay, so at this point, let's check out our next slide. How can we put all this together in an equation? Well, the zero product rule allows us to take our factors, something times something, and notice that if something times something equals 0. So if a product turns into 0, another way of saying that, a product could be A times B, right? Factor 1, factor 2. If a product equals 0, what must be true? For example, what if A was the number 2? And I said 2 times something gives me 0. What has to be true about my something, my box here, my question mark box? Yeah, that must be 0, right? That must equal 0. So our question mark would be 0. The question mark box is just like a variable, an unknown. Okay, so what we just said is we've noticed that if I have something times something and we know it turns out to be 0, one of those, or maybe even both of them, are 0. And that's what we're saying here in our words. If the product of two quantities equals 0, then at least one of those quantities must equal 0. That should make sense intuitively, okay? And we've shown you a couple of examples there. 3 times 0 would be 0, or 0 times 4 would be 0. So if A times B equals 0, then either A equals 0 or B equals 0. I got tongue-tied there. So one of them must be 0. They could even both be 0. All right, so why am I telling you all of this? Well, suppose that we had a situation where we had this polynomial x squared plus 7x. And this will represent, we're going to learn in our future days together and videos together, we're going to learn that this represents a graph that looks like a parabola. Maybe you've heard of that before. Maybe it's a bad memory, but it's going to come back soon, okay? And what this represents is a trajectory that has high degree of symmetry. So if you were to cut it in half, it's actually the same distance from this line in the middle, called the axis of symmetry. All right, so it's that's representing a type of trajectory, okay? Whenever you have an x squared and then you have two other terms potentially. Okay, so what this is saying is if I had an equation like y equals x squared plus 7x, if I knew that that was the basic shape, and then I said, let's let y equal 0, do you remember what that means? We're going to talk more about graphs in the future, but when you let y equal 0, what happens on your graph? Well, wouldn't that mean that if you had an x-axis, for example, at y equals 0, those would be your x-intercepts, right? So we're basically giving you the tools that you're going to use in the future to find x-intercepts. When you let y equals 0, which is what we have here, you're finding x-intercepts. And we're saying if it has x-intercepts, because maybe it wasn't going through the x-axis twice, maybe it was completely above the x-axis up here, and it had no x-intercepts. Or maybe it dipped down and touched the x-axis and then turned around and had one x-intercept. You could have up to 2 answers because the degree is 2. We're going to learn more about that when we talk about polynomials in detail later on in the semester. But what we notice here is I could use my factoring skills now to help me in the future. So let's talk about what that would look like. We would notice that there is a GCF here of what? X, you got it. And what would be in the parentheses then? That's right, x plus 7 equals 0. So what we now know is x squared plus 7x, which is going to eventually represent a parabolic trajectory going up, is also the same as x times parentheses x plus 7. Okay, great. But here's something cool. Because we've set it equal to 0, those are telling me x-intercepts for my graph eventually. And so what we're noticing is I have something times something equals 0. If I have something times something equals 0, we know according to the zero product rule, which is just common sense, right, that one of them has to be 0. So either x would equal 0 or x plus 7 would have to equal 0. That's a linear equation. We know how to solve those. Get x by itself using subtraction on both sides, getting rid of the 7 on both sides. X would equal negative 7. Great job. So maybe you've seen this before. Maybe it's a little rusty. Maybe you had no idea why people made you factor. There is a purpose, I promise. And one of the main purposes that you're going to be using factoring for is to find x-intercepts in graphs. So that's going to be a skill you're going to be needing to be proficient in. So factoring is not something where you can say, I'm just not a factoring person, but I'll be fine. You won't be fine. You have to learn how to factor if you're going to be successful. So what we found here is that the two x-intercepts, you didn't know this yet, but I'm giving you some secret information for the future. Your two x-intercepts are at 0 and at negative 7, which means that this graph, if this is the y-axis, you have an x-intercept at 0 and at negative 7. We now can interpret what's going on in a parabolic trajectory, x squared plus 7x. Okay, that's more information than you needed, but I wanted to give you some reasons to understand why factoring is going to be super important using the zero product rule to find x-intercepts. So once again in this video, we've talked about the GCF. That's step 1 for factoring. Always look for a GCF. And step 2, If you have 4 terms or more, try grouping. And then the zero product rule is going to be your friend from here on forward. All right, go practice because math is not a spectator sport. I'll see you next time.